today I would like to talk about boundary conditions. The last time I considered the equation. Okay, so let omega the domain in the t time, and now we consider that the Lagrangian formula of the fluid mechanics. Therefore, that phi t is a map from omega, defined omega to Rn, the smooth map. So y is corresponding to the phi ty. Another representation is yt. And now today I would like to talk about the boundary conditions. Therefore, let gamma is the boundary of omega. Then omega t is a map of omega by pt. So x equal t ty y omega, and gamma t is to x equal t sub t y gamma. This is a notation of domain omega sub t and the boundary of omega sub t, the gamma sub t. So the situation is omega is now here. And then consider the phi sub t map phi sub t. And then when time t, so this point is going to x, and so the boundary gamma t, and the domain omega t. Moreover, so n sub t is n sub t unit this is, I want to fix these notations. Okay. Then let W is now dT time evolution of this map, and then when y equal x sub t, therefore x in t y, and then the phi sub t is a smooth map and solid, and also injective. Injective smooth map. So 1-to-1. This correspondence is 1-to-1. Same as last time. So this correspondence is invertible. So x, if you give x in the Euler coordinate, if you consider the Euler coordinate, you take point x, then you can ask where you come from. Meaning is that you can find y Then y is after t, the y come to the x. Yeah. So this is a correspondence of this Lagrangian and Euler. So Euler is usually the so you are usually stay in the Euler. Then you look at the flow. Then you look at here, and then you can ask this point where you come from. Yeah. This is Lagrangian and Euler correspondence. Then the equation is given by Euler coordinate. But then the last time I gave you the correspondence of the Euler coordinate, the equation, Euler coordinate and Lagrangian coordinate. Anyway, so the last time, let be xt, and then this is the velocity field. In the Euler coordinate, Lagrangian coordinate, and rho xt, mass st, and p xt is a pressure field. These quantities are given at Euler coordinate. And then conservation of mass, meaning is a dt rho, d rho v. This is the conservation of mass conservation. Conservation. And rho dtv v number v is equal to, now I only consider the Newtonian flow. So this ds e plus external forces. And s e is half d e plus mu minus mu di minus pressure R. And mu is first viscosity constant. Viscosity coefficient. And the nu also positive. The second. So this is the Newtonian flow. So this is, sorry, so this is Newtonian. Sorry, this is momentum, conservation of momentum. Okay, and then maybe it's not necessary now to explain this one and this one. It's a tangent. It's a symmetric part of gradient V. This is a usual divergence of V. So this is the equation. Okay, and then now also we need boundary conditions. And to drive the boundary conditions, also we assume that the conservation of mass and the conservation of momentum. To introduce, to derive these equations, we also consider, we start we assume that the mass conservation and the conservation of momentum, but it is you first consider some. If you remember the last lecture, so the first we consider some fluid particle omega t, and then the omega t. So finally, in order to get to these equations, this fluid particle is shrink to 1 point. Okay. So first we fluid particle is a very artificial thing, but anyway we consider the fluid particle, and then we assume the conservation of mass and the conservation of momentum, and then you get to these equations after shrinking the fluid particles to 1 point. But today I want to drive now omega t, omega. We don't shrink the omega. And then also the omega t. Now we again assume the mass conservation and the conservation of momentum. And then these quantities how affect the boundary conditions. Therefore, we don't shrink the omega t. Omega is fixed now. The omega sub t is also fixed. We consider some float. And then, okay. So the situations are a little bit different from the last time. Now this is fixed. I'm sorry, right here. Okay, then what? Then that's W. It's now dt. Already I wrote, sorry. But then now today, W sub t is this one. So it's really the velocity of evolution of omega t. And then last time we assumed that this is bxt because we consider the fluid particle. Therefore, this is equal to this one. But now is the domain is fixed. And then we consider in here is fluid. The V, rho, P. So the evolution of omega sub t and the flow velocity field is we assume that different first, different things. Okay. Because, yeah, not so easy to think about, but omega is moving. And then in the omega, also fluid is there. And then it is the different, finally, viscosity gives the same speed, but from mathematical point of view, it's different. Then, again, the conservation of mass. First, we consider the conservation of mass. This is ddt omega t rho dx is equal to 0. This is the definition of the conservation of mass. So this integration is a total mass of this fluid fluid occupied omega sub t. And then by by Reynolds transportation theory called ddt rho plus div rho now w dx. Last time v equal w equals same, therefore here is p, but today the w is this one. So if you look at the first line of the mass conservation, so v and w equal different. This is because of the Reynolds. We use the Reynolds transport equation theory. Just time derivatives enter here, and you get this one. But then now use here is dt rho is equal to minus div rho v. Therefore, you get omega t rho w minus t. This is zero. Okay. And then divergence theorem of Gauss is just this is go to the goes to the integration on boundary. Divergence is changed to the multiplication sub n sub d, and then d omega. D omega is a surface element. Yeah, so sometimes a mathematician is very serious about the definition, but so far you just consider this formula. It's not so necessary to think about the rigorous definition of this elementary surface element. Okay. This formula. So the bulk space and the boundaries are connected in this way. So divergence is go to the normal component. Normal to the gamma t. And this is a surface element. And then now this is zero. Yeah. So we may assume that this is zero. So we can derive but of course rho is positive. And then you don't need this one. So first assumption is this one. This means that gamma t just evolution speed of omega t and the velocity field the same coincide at gamma t. So the body is evoluted, but then the fluid has the same evolution at gamma t boundary. This is so-called no-slip condition. Otherwise, you have some vacuum here. If the evolution of body has a different speed as fluid, then for sometimes you have vacuum here or overflow if speed is different. But then usually we don't observe such things. We expected at least the domain and fluid has no slip, no vacuum, no overflow. Okay. So this condition guarantees that the no-slip conditions. It's really necessary, but the important conditions, kinetic, other ones kinematic. So when we consider fluid as a boundary, if boundary is moving, then you have to assume this one. Okay. Of course, you also consider the non-moving. I mean, just a fixed domain. Then it's, for example, velocity field is zero on boundary. For example, it is so-called Dirichlet conditions. This also the guarantee non-slip. Yeah, because the boundary is fixed. So at the boundary, at least the normal component of U should be zero. Right? But this is non-slip conditions for the fixed boundary. But now we consider just the boundary is also moving. That case, this is necessary conditions in order to get non-slip. I mean, no vacuum, no overflow. So the physical situation is the typical physical situation is the bottom is fixed and over is a free boundary, like ocean or something like that. Yeah. So the bottom is a fixed boundary. Then here is gamma t, so you need the free boundary condition on the surface. Okay. Later I give you more details. But anyway. So usually we write this one. It's an evolution. And then the important condition is free gamma t. This is important. And the another representation another way to represent this formula is, for example, the gamma t is given in this way. This is also typical things. It's gamma sub t is usually n-1 dimensional surface. So mathematically, locally, this surface is given by in this way. Right? The usual. Okay, then x equal y sub t, y on boundary. Therefore, you differentiate this formula. And this is dtf plus gradient and now this is w notation, but you know that n sub t is from this representation, then it is this is the unit outer normal is given by in this way. Okay. This is elementary geometry. Therefore, we know this. We assume this. Therefore, just you multiply this one. So the w x you have this formula on f equals 0. So here is instead of w, you can use v. So another formulation of the kinematic condition, no-slip condition. Is rho t. Sorry, I'm sorry. dtf plus or f equals this. So this is another representation formula of our kinematic condition, non-slip condition on boundary. This is also sometimes we can see this condition on a paper concerning the rebounded problem. Rebounded problem is a very popular problem for the engineering people. So, because therefore, I think some of the people come from the engineer. You know these conditions. This is conservation of mass. Now, second, Next we consider now consider the conservation of momentum. So formula is this one. Sorry, maybe each component. So the velocity field of this is the representation. So Vi is ith component of velocity field V. This is a conservation of momentum. So this again by the Reynolds theory, we can write inside the d dt rho Vi plus divergence rho Vi W. It's a Reynolds theory. Okay. Now the procedure is the same as before. So now we use the we know the first term is Vi et rho. So plus we write Vi is outside rho W, and then rho dt Vi plus W lambda Vi. Just to we differentiate these two terms. And then by using the mass conservation equation for the mass conservation, first term is Vi rho. Okay, this is by using the equation of mass, the conservation of mass, equation of the conservation of mass. Yes, the same as before. And then yeah, we know that the equation of now okay, sorry, S okay, and then we use this notation. Now I forget. Now we forget the rho f. We consider rho f equals 0 case. Therefore, this is this. This is the vector representation. Then each component, ith component, the dvi cross B over BI is equal to divergence this ith component. Yeah, okay. And then S is d mu du dv plus mu minus mu divergence bi minus bi. Sorry, maybe to understand the Navier-Stokes equations, first maybe you understand the representation of the tensor. So if you write the ij component of S, then from this Sij is mu dij d plus mu minus b. This divergence b is scalar, so the delta ij minus d delta ij. So this is ij component of n by n matrix of S. Okay. So now S is right in this way. Okay. And Si is this one. So okay, S so S is from this divergence. Well, each SI is n vector. So you take divergence SI is just you take this div S1 to Sn. So the divergence with chapter D is take divergence for each component. So D. This is notation, in some sense notation, my notation, but not my normal notations. Okay, therefore, if you remember this one, then this div I is just the div I. This equation is written by div I. So, right? Okay, therefore, by using this notation, Now, this is the starting point of law. So B VI. This, and then now I want to represent this part. Yeah, please. I want to come back to this here. And then the first line is we use the conservation of equation for the conservation of mass. So dt rho is given by div rho w, therefore it's minus. Dt rho is minus div rho w. On the second part, now we use dtv plus, so, okay, so dtv, now we use this one. Therefore, dtv is rho w minus b vi plus div si. Oh. Now plug this formula into here. Okay. And then now here it is. You can these two terms you write divergence. So, is equal to t if rho w minus b vi is faster. This two is come to here. This one. Yeah, because if divergence come to here, then this is a vi div one. And then divergence come to here, it's nabla vi. So nabla vi rho w minus b. And the second term is omega t. Yes. Now, again, I want to say that we assume that the rho is zero. External force is zero. Yeah, because we consider the conservation of mass. If external forces is non-zero, then you don't get the conservation of mass, conservation of momentum, excuse me. But now we consider the rho f equals 0 case, then we expect to get the conservation of momentum. So this is zero. This is zero. This is conservation of momentum. This is zero. Under this assumption. We consider the Newton law. Then, again, we use the Gauss theory. We It's by Gauss. And then already by conservation of mass, we have 0. It's by conservation of mass. So finally, we have gamma t is lt, the omega is 0. This is conservation. Momentum. This is the ice component. I now again I use a vector representation. So as a boundary, if you consider the conservation of momentum, then the suitable boundary condition should satisfy this condition. So requirement for the boundary condition is this one. For the to keep the conservation of momentum. But okay, so first simplest one is of course this one. On gamma t. So this condition is just a point-wise condition. This is the simplest case. But requirement is just integration on gamma t must be 0. Therefore, we can consider the different one. Meaning that we also the second one, t is some g on gamma t. And the requirement of g is this one. Okay. So in some sense, you get some external forces on boundary. Then in order to keep the conservation of momentum, the external forces on boundary should satisfy this condition. This is another mathematical requirement. Okay. So if you consider some problem, more concrete problem, then you have to consider the external forces on the boundary for the fluid. But then the suitable boundary condition, suitable external forces should satisfy this condition mathematically. Okay. So this is a requirement if you want to keep the conservation of momentum. This conservation of momentum is a very physically natural condition. Then, what is a typical G? Is surface tension. So there are different ones, but for the typical example, G is a surface tension. Ending is a sigma. Or the capillary, another word is the capillary forces on the boundary. So on the boundary gamma t, we consider some of the capillary force. So it's a water here. It's water. Then a capillary effect gives you some of this kind of figure of water on the top. So capillary forces are very natural forces for the fluid. So capillary surface tension. Surface tension gives you this kind of figure of boundary of omega. This is free boundary, right? Here. Water. This is cup. Or top of cup, you have this. Then now I don't explain how represent this capillary forces, but maybe later when we consider some problem, surface tension problem in mathematics, I give you more detail over this. But now, okay, H gamma T LT is given by Bertrand operator on gamma T. X represents the point of gamma sub T. And then the capillary, this H, sorry, H gamma T will represent -1 fold mean curvature. Gamma T. And gamma T is the Bertrand operator. When we will consider some capillary problem, I give you the more detailed definition of these quantities. So far, now just I give you this formula. So n-1 fold mean curvature of gamma T. Mean curvature is just represent some of the how curved the gamma T. So one of the way to represent how curved the gamma T is to use mean curvature. And then this mean curvature is given by the Laplace-Bertrand operators. I will give you later. I will give you these formulas, but now today is just announce you these formulas. Okay. Therefore, and of course, this condition is now G the omega. Now this is sigma gamma T LT d sigma d omega. This is given by Laplace-Bertrand operator of d omega. But the gamma T has no boundary. I mean, it's n-1. We assume that n-1 manifold in manifold. So without boundary, it's just like this, like circle. Therefore, this is 0 because this is a Laplace-Bertrand Laplacian, and then by using the usual this is a surface, therefore there is no boundary. So its integration by parts is 0. Okay, so 1 times this one, so integration by parts going to gradient here, then vanishes. So surface tension satisfy this condition. Maybe I don't know other examples, but the surface tension is mathematically very important. Therefore, yeah. Okay. So the free boundary problem. I mean, you consider the fluid, and here is the gamma t is a free surface. Then you can consider the surface tension of the gamma t. The surface tension gives, if the surface tension is, for example, this case, so convex, the free surface is convex, then the surface tension keeps the shape of boundary. But if the surface is, for example, this, some part is non-convex, then unfortunately this is going to, the time evolution is, so surface tension doesn't give you the stable shapes of the boundary. Usually, mathematically, the final is going to two parts. But we cannot consider this is an analysis because the shape is different. So the classical analysis doesn't explain why this finally come to this one. Classical analysis doesn't we cannot use classical analysis. It's a more done. I don't know. I never thought about this one. Just we know some by experience. Experiment we know this one. But mathematically, no, rigorous mathematics cannot explain this one because of the topologies are different. Okay. So mathematically, my lecture is only consider these shapes. Then this case is the surface tension gives you the stable surface, stability of the surface. But if you are very interested in more applications, then you can use some of the numerical analysis. Maybe numerical analysis gives you this. I don't know. Okay. But anyway, here the important thing is the surface tension satisfies these conditions. Okay. So you can consider the surface tension also on the free boundary. The surface tension keeps the conservation of momentum. All right. Now I will go to the more rigorous mathematics, but before going to this, today, the rest of time, I have still some half an hour remains, but from my operation, it's not necessary to use this half an hour. More, two more conservation I will talk about. So it is another one is a conservation of angular momentum. This is angular momentum is in Japanese or in Chinese. And also, sometimes it's very important to use this formulas. I forget the English. Could you tell me? Ah, center of gravity. Yes. Center. So the center of gravity is the differentiation in time to become this one, momentum. Right? Thank you. So this is also a rather fundamental relation. Just calculation. This is much easier than first. So Reynolds, of course, you. Now for simplicity, we are assuming that okay, of course, sorry. So of course this is this hold under this assumption. And of course this is the usual situation. Sorry. No. So of course xi is independent of time. There is maybe no, something instead. So then if divergence counted here. Size independent of time. This is just a DT1. But here is the divergence apply here, and also to right here. So you have two terms. And then this is zero. So conservation of mass. This is zero. the relationship of the center of gravity and momentum. How we consider the conservation of angular momentum? This is we use the Reynolds transporter equation theorem. So there's cos dt. So that's sorry. Now angular momentum. This is an ideal component of the angular momentum. Xi dt minus x di is ideal component of the angular momentum. And also we assume that so just so video sorry. My calculation. I don't use this one. But anyway, conservation of mass for the finally so of this formula. Verify that. Okay. So. There's also you can write in. It's very much complicated. Excuse me. Yeah. Let's keep this. Nothing wrong. There it is. So this is J. This is correct. So it's good. Intermediate with I confuse some I and J. But I guess this is correct for that. I hope. And then that sum is 0. This sum is bounded. Formula vector. So this is scalar. This is vector. The give is changed to empty. We are sure that this is 0. Example, first sum. So we only have the second sum. Then what is now we write this otherwise minus xi I is j plus st1. This is vector. So I write so nice. Sorry. This is just you take the diagonals from outside. And you have to eliminate SJI. Then Sij is symmetry. This is symmetry. And for this bunch. You remember Sij. Yeah. So Sij is a symmetry. So we have by our formula. Of course, we consider if in this case, then this is 0, right? This is 0. We are sure of this one. And second is sigma this. This is gamma t xj minus xj gamma t xi. This is just j's component. J's component. So if you write this j is so nth component of this mt is nth component of this one. X is point. Ith component of this is delta n gamma t xi. So here is this one. And then Laplace operator they usually diagonal now. This is the same even for the Laplace Bertrand operators. Maybe later give you the definition, but anyway, now today please believe that Laplace Bertrand operator given by divergence of gamma t and the number. So div number 4. Therefore, you make integration by parts. Sigma minus nabla gamma dxi in the product nabla gamma dxj. And this in the product is the same, therefore. This is a proof of the conservation of angular momentum. Okay, so thank you.